15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Hello again, and thank you for joining us on Space Nuts. It's all about astronomy, space science, and you name it, all sorts of amazing things. And we've got a jam-packed program for you today. We'll do an update on the James Webb Telescope. Things are going well at the moment. Systems are nominal. We're also going to look at the mystery of a dimming star. Now, quite often you can figure that out because something gets in the way, but this one is proving a little bit hard to define. So we'll look into that. And size doesn't matter. Yes, you heard it first. Size doesn't matter. Space Nuts can make that an absolute. We're talking about when it comes to an extinction level event, like something big, rock-like, hitting Earth. Apparently the size of the rock is not the issue, and we'll explain why. It's a fascinating story. Plus a couple of questions. We're going to look at a question from Nick about Proxima Centauri, and Alex wants to talk about detecting big rocks that hit planets and destroy them in light of the new movie called Don't Look Up, which I actually watched a few days ago. So I'm looking forward to talking about that. And we've been sent a joke. So we'll finish the program on that, and that'll be the end of us because I don't think anyone will tune in ever again.
But this program is a joke, Andrew.
Sorry?
This program is a joke. Everybody knows that.
I don't know who that was. My name is Andrew Dunkley, and as always, joining me is Professor Fred Watson, astronomer at large. Hello, Fred.
Interrupter in chief. Sorry about that. You were just about to introduce yourself. Anyway, never mind. We know who you are. Yes, I'm very well, thanks. How are you?
I am well. I am well. Just ignoring the news headlines that just popped up showing that over 50,000 people in New South Wales and Victoria alone have now been proved to have COVID. We'll just not bother with that for the moment and get on with our lives.
Indeed, we should.
Now, Fred, let's just kick straight into our first story, and that is an update on the James Webb Telescope. It is all good news so far.
Yes, that's right. There has been progress. The latest we have is that all is going well. In fact, the technical description, which comes from one of the lead engineers at Northrop Grumman, that's the prime contractor for the telescope, the technical description is that everything is hunky-dory. There you are. So that's it. There were issues, though, Andrew. I don't know whether you caught up with this. There was an issue with the sun shield. Now, the sun shield is a critical part of the telescope because without it, it fails. It doesn't work. It's this tennis court-sized set of screens that have to be deployed, and they deployed perfectly well. But the unfurling them is only part of the story. Then they've got to be stretched tight across their sort of framework. And there was a glitch in that because apparently some of the motors that were involved with that were overheating, 6 of them apparently. And that was seen as, there wasn't a problem with it, but that was seen as a potential issue. So they turned the telescope to stop the sunlight falling on these motors, and the motors cooled down, and the kind of tightening up of the sun shield, or securing it as it's called, which is apparently a 3-day process, that continued. And I think that finishes today, and maybe tomorrow US, maybe tomorrow Australian time. Anyway, it's very, very much the kind of time frame that we're doing this podcast in. So that's everything's checking out okay. As you said, all the systems are nominal. There is a nice quote as well from Bill Ox, who's project manager. He said, the best thing for operations is boring, and that's what we anticipate over the next 3 days, is to be boring. They don't want anything going wrong, which causes excitement. Boring is good in missions like this, where you're trying to set the thing up. And they do. The reports I've read suggest that the mission controllers might actually start unfurling or unfolding the mirror as soon as this weekend. The 18 segments of the mirror, not all of them have to move, actually. Quite a few of them are already in position, but the outer regions of the mirror have to be unfolded. And of course, then you've got to make sure that these segments all align with optical perfection, because it's got to replicate a single mirror, the diameter 6.5 meters or 21 feet. So
it's been a remarkable effort so far, I must say. And I know there were delays, but they had to get it perfectly right, because, as you and I have discussed, once it's there, and if something goes wrong, they cannot fix it. So everything has to work perfectly. And you talk about a critical thing like unfurling the mirror, but everything they do is critical in this process. And you've got to give them a big tick for being able to come up with a solution to the overheating motor problem. Just swing the thing around away from the sun, cool them down, unfurl it, swing it back. Yeah, all solved.
Yeah, that's right. Brilliant. Well, that's the sort of resourcefulness that you expect from these things. So yes, you're right. It's on its way to its destination, the L2 point, second Lagrange point, 1.6 million kilometres or 1 million miles beyond Earth. And I've been guilty, Andrew, of oversimplifying the reason why it's going there. And in fact, I've said the wrong thing in some past conversations, because what I said was that the telescope is in the Earth's shadow, and that's not the case, because at that distance the Earth's shadow is not big enough to cover the sun. So what it is, the reason why it's gone to L2, that Lagrange point, is it's all about the thermal, the heat flow on the telescope and things of that sort. But it's an odd thing. You've got this imaginary point in space where gravity essentially is nulled, but you can orbit around that. You can actually put something in an orbit around this imaginary gravity null point. And that's what's happened with other spacecraft like Gaia and I think the Wilkinson microwave anisotropy probe was also at the L2 point. But so you can do that. You can orbit around this point, which is what the James Webb Space Telescope will do. But the reason for doing that is because from that position, you've got a very, very stable and constant heat load on the telescope. You're not in the shadow of the Earth. You're still in sunlight, but it's constant. It's not changing as you orbit around the Earth as it would. Basically, because you're going in an orbit that is parallel with the Earth's orbit, and takes you round in more or less in the same time as the Earth goes round. So you've always got this constant direction and distance to the sun, and that gives the telescope's operators a stability, which is what you need to operate an infrared telescope of such exquisite sensitivity.
Yeah, I did actually see an animation the other day of the way the James Webb Telescope will behave, the way it will move when it gets to L2.
Yeah, yes, that's right.
Extraordinary.
It is. That's right. Yeah, there's a bit of it's almost like 3-point turns and things of that sort in the orbital trajectory. Yes, that's correct. Anyway, I do apologise for misleading comments I may have made on Space Nuts in the past.
All good and well, Fred. Let's move on to this little mystery, because we'll have more to talk about this year as things develop with James Webb. But this little mystery is about a star that has been dimming, and quite often, in fact most of the time, they can say, yes, we know why that's happening. This, that or the other has occurred. This one's proving to be a little bit more complex.
It is. This is something that it's an object that was detected by the TESS satellite. TESS is the Transiting Exoplanet Survey Satellite, a NASA mission that has been finding exoplanets, and very good at it too. So it is one of the objects detected by TESS. It's quite a long way away. It's 2,300 light years away. And so its light varies, which is what TESS is all about. It's all about detecting this variation of light, and particularly as a planet passes in front of its parent star. But what they've discovered is for this object, and I've got to tell you its name, Andrew, it's TIC 4007992224.
Okay.
Don't forget that.
I already have.
So there's a basically its light was seen to drop by 25%. This, I think, is 6 years ago when they started observing this thing at first, over a period of hours, and then with sort of variations in brightness following that, and that was interpreted initially as an object that is breaking up or releasing dust, because we've seen those things before. We've seen things that look like planets but are actually objects that are in the process of breaking up. So they obscure the light from a star, but they just gradually dissipate. The star Fomalhaut has an object like that orbiting around it, a bright star. What they've done is they've now got 6 years of data on this object, and they find that it's not really as simple as that. And there's a number of complicating factors. One is that this star is not a single star. It's actually a binary star system. So it's two stars in orbit around one another, and that complicates things. But one of them is also a pulsating star, which complicates it even further, with a 19.77 day period. And that's, a strong level of periodicity. But whatever it is that's dimming the light, on top of all that is something that it's apparently quite erratic. That's the word that's used in the report I read, which comes from Science Alert. The erratic behavior of this light, and it actually suggests that is perhaps an orbiting object that's emitting clouds of dust. But the reason why this is still a puzzle, Andrew, and I should say this work's been done at the Harvard-Smithsonian Center for Astrophysics. The reason why that's still a puzzle is that it's huge quantities of dust that are being emitted to cause this dimming of the light. And if it was just a body itself that's falling to bits, like, for example, one of the asteroids of our solar system doing that, it would not be emitting the same quantities of dust for 6 years because it would have a short lifespan, probably longer than 6 years, probably more like thousands of years. But it's still, you would notice that was changing. That that if it was an object that's disintegrating, you'd expect it to dissipate, and eventually the periodic or the quasi-periodic dimming would stop, and that's not happening. And so there is a puzzle which is not really easily resolvable, because for a start, you don't know which of these two stars in the binary system this object is orbiting, and so you get a different percentage of the dimming depending on which star you choose. It can be either 37% or 75% of the light from the parent star, depending on which of the two it is. And that's a lot, that's a large amount of obscuration, particularly the 75%. And so the most likely explanation that this group from the Harvard-Smithsonian Center for Astrophysics have evolved is that something around something around going around the star, a planet-like object, is colliding with something else as it orbits and releasing a dust cloud every time it clouts this other object, so that every time it goes round, there's this impact between, perhaps a planet-sized object and an asteroid-sized object that releases a new cloud of dust, and that's the only thing that they think fits the bill. That it's got all the other things that they've suggested, which include disintegration, which we just talked about, the possibility of a dust cloud which is being shepherded around by a planet embedded in the protoplanetary disk, or the protoplanetary disk itself doing weird things. They've kind of ruled all those things out. And just ended up with this idea that maybe there are two objects that are actually colliding. It's one of these things that will need more and more observations to get to the bottom of the story.
When they've found these things in the past, what has usually been the cause?
Well, there's not been anything quite like this. Usually it's a much more, you've got something where the obscuration changes slowly over time, and you can envisage that would be caused by a dust cloud dissipating as time goes on. If you got dust released from a planetary surface, excuse me, for example, then that cloud might be thick and quite dense when it's first released, but as it spreads in space, it will get more transparent. That doesn't seem to be happening with this object. The thing is reasonably bright. I haven't got a note of its brightness, even though it's quite a long way away. So it does raise the possibility of there being more observations made of it,
so
other observatories.
I'm going to give this potential reason a name. It's ROC, R-O-C, and I've forgotten what that was going to stand for now that I've defined it. Regular orbital collision.
Oh, I like that. Yeah. It's a rock.
Regular orbital collision.
We should send it to the.
Should send it to them and say, here's what you can call it.
You can call it that.
Turns out to be that. Like that.
Or it could be.
I better write it down because I'll forget otherwise.
It could be
I should record this so that I never forget anything.
Somebody will. Don't worry about it.
I've written it down now. All right. Well, maybe in a future episode we'll be able to turn around and say, well, it turned out to be a rock, a regular orbital collision. Seems to be the most likely reason.
Actually, another one that's a possibility is a Durdis. It could be a Durdis. A Durdis, a dusty object erratically dimming its star, which is the title of the report that we've seen. Yeah. Anyway, that's enough of that. Yeah, I think rock's better than that. A Durdis is not terribly intuitive. No.
My idea's got it's a bit more solid.
Oh, a bit more solid, yes.
All right.
I'd say rock solid, actually, Andrew.
Very. Oh, dear. What were we talking about? Can't remember.
No idea.
You are listening to Space Nuts with Andrew Dunkley and Professor Fred Watson.
Roger, you're loud and clear here also.
Space Nuts.
Now, if you're into social media, I remind you that we do have an official Facebook page. So if you use Facebook, jump online and just do a search for Space Nuts. And we've got thousands of people who follow us on the Facebook page. And we publish a lot of material there for you to peruse. There's also the Space Nuts podcast group on Facebook where people talk to each other that listen to the show and share their astronomical photos or ask questions of the audience, and everyone has a crack at answering those. So, we're well entrenched in social media, and of course we recently joined Instagram as well. So if you're an Instagram user, spacenuts.io is our username there, and we'd be happy for you to follow us on Instagram as well. Now, Fred, to our next story, and this one I love. Size doesn't matter. Now, what we're talking about here is something hitting Earth. Now, in the past, there have been extinction level events where something's hit Earth, and it's happened more than once. I suppose the most famous has been the Chicxulub crater asteroid, which basically was the end of the dinosaurs. It polished them off. I think they were already on their way out from other studies that have been published, but that's the one that basically did the job and caused a global extinction event. But we all assume, and it's just a natural thing to think, that it's the size of the rock that hits the Earth that's going to cause an extinction event. So if it's a smaller rock, no big deal. That apparently is wrong.
It is, and the reason why researchers have actually homed in on this to try and understand it is because impacts which we know about from the cratering record on the Earth, there are some impacts that you would expect to cause mass extinctions that don't, and some that you wouldn't expect to cause mass extinctions that do, if all you were looking at was the size. But actually, it's not that at all. Clearly, size is going to play a part in it because that's the amount of energy that's being put into the rock. But something that is perhaps just as dominant is what the meteorite hits. What is the rock that it actually collides into on the Earth? And it turns out that if you hit rocks that are rich in a mineral rock called potassium feldspar. Now, feldspar is the commonest rock on the planet. Huge percentage of the surface crust of the Earth is feldspar, but feldspar comes in different varieties with different elements that are actually bound up in the crystal lattice in different ways, giving it different characteristics. And the researchers that have done this work, who are actually based in Liverpool in the UK and Tenerife in the Canary Islands, what they've identified is the potassium variety of feldspar. Potassium feldspar, if you've got rocks that are rich in that mineral, then you get a mass extinction event. And that's an extraordinary discovery. It really is an amazing discovery. Because it seems so straightforward that the bigger the impacting objects, the more energy there's going to be and the more damage there's going to be. But there is this other really important constituent. And so, well, let me just quote from one of the authors of this work, Dr. Chris Stevenson, who's University of Liverpool's School of Earth, Ocean and Ecological Sciences. He says, for decades, scientists have puzzled over why some meteorites cause mass extinctions and others, even really big ones, don't. It's surprising when we put together the data. Life carried on as normal during the fourth largest impact with a crater diameter of about 48 kilometers, whereas an impact half the size was associated with a mass extinction only 5 million years ago. Many kill mechanisms have been proposed, such as large volcanic eruptions, but just like meteorites, these don't always correlate with mass extinctions. Using this new method for assessing the mineral content of the meteorite ejector blankets, that's the stuff that comes off when the meteorite hits the surface, we show that every time a meteorite, big or small, hits rocks rich in potassium feldspar, it correlates with a mass extinction event. This opens up, there's a really interesting comment that Chris Stevenson makes. This opens up a whole new avenue of research. What exactly kills off life during these episodes, and how do the potassium feldspar effects last? Until now, only meteorites have changed the aerosol regime of the climate. And that's the trick, apparently, Andrew, with this, that it's the fact that potassium feldspar causes raises aerosols that changes the cloud cover of the planet and actually lets more sunlight fall on the planet and warms it up. So what he's saying is, just picking up the story from Chris, until now only meteorites have changed the aerosol regime of the climate. However, present-day human activities represent a similar mechanism with increasing emissions of mineral aerosols into the atmosphere. So a really interesting and fundamental paper that has just came out at the beginning of last month, and really, almost rewrites what we know about meteorite impacts.
Would it be possible for us to be able to, okay, we know this is going to hit us. Would they be able to calculate exactly where and then say, oh, that's okay, that's a benign target, we'll let it hit Beijing? It's cool. Won't cause a mass extinction event.
Yeah. Well, with enough warning, you can predict where an object's going to hit on the Earth. And yes, maybe you can predict whether it's going to be rich in potassium feldspar. It's sometimes, by the way, called K feldspar. K is the chemical symbol for potassium. But I think anything like that, you would actually you would always take civil defence action, no matter where it was going to hit, because it's all well and good having scientific research results like this, but who knows what might happen in practice. There could be other things that come into play that we don't know about yet.
Now, when they say mass extinction event, they don't mean that the whole planet has seen an extinction occur, because I think there have been 5 global mass extinction events in the history of the Earth that we know of, and only one of them, I believe, was caused by an asteroid, and the others were caused by other factors.
Yes.
So are these sort of localized effects that we're talking about?
Yeah, they are. They're more. They're not necessarily global effects. So you get a change in the ecology of a whole region. Maybe even a whole continent. That's the kind of thing that they're talking about.
Okay, so so people probably don't even think about small scale events like that. You assume that if something's going to hit the Earth, it'll be a global catastrophe. But I think you and I have talked about certain sized rocks.
Yes, exactly,
and the impact effect and. The explosive nature of them, and how they could destroy a city or a region or a state or a whole country, but not the whole planet. So, but this sort of changes the game, because it doesn't matter about the size of the rock. It's what it's hitting that could be the deciding factor.
That's exactly right. It's just added a new layer to the whole issue of asteroid impact.
It's also increased the odds.
Yeah. Indeed,
just
right.
what we wanted to know. You
Yes.
can all sleep at night knowing that there are now higher level of opportunities for
mass extinctions. Yes, yeah.
Oh dear. Okay, well that'll help.
That's a cheerful thing, really.
Of course, we've got questions coming up soon. We answer questions from time to time, but a couple of questions have come in about detection processes and the like, and we've talked about those many times. This to sort of add a reassuring element to this. These things are heavily monitored, aren't they?
Very much so. Yes, they are. It's a big, it's almost an industry is searching for near Earth objects, and as we'll talk about when we get to question, I think I'll say a bit more detail about that then.
Something else that slipped my mind. I was told today I had a very bad radio shift. I was all thumbs, and my program director said to me, it's because it's windy. People don't think straight when it's really windy. And I said, well, that's interesting. And I think it's still happening. Still happening today. Yeah, it is very breezy here today, so that may be the reason.
That could be it. It's because it's windy, Andrew. Don't do space nuts on a windy day.
Too late now.
Yeah.
Too late now.
Too late.
All right. But it does fascinate me, and I guess the final question I have is, do they know where these pockets of mineral are on the Earth? Has that kind of thing been mapped?
Yes, I think the answer is yes. The Earth's geology is very, very well known partly because of commercial interests. You want to know what's there so that you can see whether you can mine it. So, yeah.
Well, if an asteroid or a meteorite hit our part of the world, we'd get a lot of gold.
Yes, you would, yeah. That'd be nice,
gold-rich region.
Yeah, that'd be lovely.
They've actually just found more down the road from us, about 50 kilometres down the road at a town called Wellington. They've just found another outcrop, if you like, of gold. So pretty exciting time. All right, we'll leave it there. This is Space Nuts with Andrew Dunkley and Fred Watson.
0G, and I feel fine.
Space Nuts.
Now, if you would like to become a patron and financially support the Space Nuts podcast, just send me a personal check or a money order. I'll give you my address. Or you can go onto our website and you can do so through Patreon or Supercast. All the information's there on the Support Space Nuts button. It's totally up to you, of course. Or you can click on the Buy Us a Cup of Coffee link, which enables you to make a one-off donation. That could be something you'd like to do, or you could support us in kind by leaving a review on whatever platform you listen to us via, whether that's Apple Podcasts, Google Podcasts, iTunes, iHeartRadio, Spotify now allows you to do reviews. There are so many platforms that we are available on, and I don't know which one you personally use. I actually mix them up a bit. But if you want to give us a review, we'd greatly appreciate it. It helps to spread the word about Space Nuts, so that'd be terrific. Now, Fred, let's move on to some questions. Got a couple of fresh ones, some fresh meat at last. Now, we've got a question from Nick, who's in Paris, but Nick's an Aussie. I'm guessing he's just trapped over there because of COVID, but probably not. Hi, Professor Fred and Andrew. Thanks for all you do with Space Nuts. It's the podcast highlight of the week for me. He obviously doesn't listen to any others. I have two questions, but they're both related, so perhaps more like 1.5 questions plus GST. A tax joke. Love it. That's not the joke I'm going to tell at the end, by the way. How do we know that Proxima Centauri is the closest star to our own? And how sure are we that it is the closest star? I see where you're coming from. Thanks again from an Aussie in Paris. Oui, happy to help. Okay, Fred, how do we know Proxima Centauri is the closest star to our own?
Because we haven't found any closer. That's the bottom line. Measurement of star distances is done by parallax. That means that you get a slightly different view of the star when the Earth is on one side of its orbit from the view that you get when the Earth is on the other side of its orbit. That the nearer the star, the easier that is to measure. You get it to a greater accuracy the closer the star is. So its distance is well known. As I said, there hasn't been a closer star that has been found. Now, Proxima Centauri is a red dwarf, which is the dimmest kind of normal star.
It's very, very insulting, but anyway, carry on.
It's an astronomical name, which is. It's not inappropriate in an astronomical context, let me put it that way. So red dwarfs are the dimmest normal stars that we know about. And so the fact that the nearest star to us is a dim one suggests, or the nearest known star to us is a dim one, suggests that there aren't any even dimmer that are nearer. And the dimmer stars are things that we call brown dwarfs, which are actually failed stars. They're not normal stars in the sense that they've got, nuclear fusion taking place in their centers. They do have nuclear reactions. It's something called deuterium burning. That gives them a signature in the infrared. So that's how you detect brown dwarf stars. They are, as I said, dimmer than the red dwarfs. So if there was a brown dwarf star that was nearer to us than Proxima Centauri, we would know about it now with the technology that we have today, because we can measure very accurately in the infrared. And it sort of raises the question that when you think about these really cool objects, I mean, at the bottom end of the scale of brown dwarfs, you get the free-floating planetary objects. They are low-mass objects. I think brown dwarfs have got to have a mass more than 13 times the mass of Jupiter in order for them to be classified as brown dwarfs. But objects smaller than that, free-floating planets, which usually also emit infrared radiation because of actually nuclear fission going on in their interiors. They might be the kind of thing that the James Webb Space Telescope will detect when it comes into action. So there may be objects that are nearer than Proxima Centauri, but aren't normal stars. And free-floating planetary objects would be one of the one of the possibilities. They're things that are often abbreviated to FFLOPs, free-floating planetary objects, but more commonly known as rogue planets, actually, or orphan planets. Yeah.
So the odds of us finding a star other than our own that is closer than Proxima Centauri are probably very low.
Very low indeed. Yes. If not zero.
If not zero.
Just because that the region of space between ourselves and Proxima Centauri is well explored, and it's nearby. It's things show up in that region. Most of what we're looking at is much further away than that, and even these rogue planets, the free floating planets, they are. They're often seen at much greater distances, more than 1,000 light years. So if we can detect them easily at those sorts of distances, we should be able to find them on our doorstep effectively.
All right. There you go, Nick, and hope all is well in Gay Paris. Now take your baguette and wrap off. No, I'm kidding. I just wanted to say it. I'm going to do a little segue to the next question, which I find works well. I've just finished watching the Netflix series Lost in Space, which, Will Robinson and the Robinson family, they kind of rejigged it into a new series, which has run for 3 seasons. It's just finished. And it's based on an extinction level event that happens on Earth, and so select people are leaving the planet to move to another planet near Proxima Centauri. Fascinating, and I enjoyed it. Now, the reason I say that is because that's a TV show, and I'm about to talk about a newly released TV show or movie, which I've just watched. And this comes about because of a question from Alex in Perth. Hi, Andrew and Fred, long-time listener and lover of the show. Congratulations on the run so far. I'm exhausted. And keep up the fantastic work. But first-time questioner is Alex. In light of the new movie Don't Look Up and the current DART mission, what defences does Earth currently have in place to deal with near-Earth objects, and which countries are responsible for them? Many thanks, and here's to many more years of Space Nuts to come. We hope so, Alex. We kind of touched on this earlier because we were talking about the extinction level events and how they could occur now that we know geology plays a big part in it. But I suppose just to fill in a bit of a blank, because I am 100% certain, or is it 98.7% certain, that Fred hasn't watched this film.
Yes. Don't
Look Up stars Leonardo DiCaprio and Jennifer Lawrence, and I'm absolutely disgusted with the producers for making Jennifer Lawrence look like such a bogan. But anyway, it's based on the fact that the Earth is going to be struck by a rock between 5 and 10 kilometres in size. It is definitely not going to miss. And the scientists have gone to the president to tell her, played by Meryl Streep, that this is going to happen and the Earth is doomed. And they received the information with we'll get our own people to look into this. We don't believe you. And the whole story unfolds from there because the scientists are saying this is definitely going to happen, and the politicians are saying, yeah, probably not, maybe not. And it's really frustrating. Now, it is a comedy. It's not a, gut-splitting, hilarious comedy. It's more of a dark comedy with a really good ending, which I won't spoil if you haven't seen it yet. But I think you'll be amused. But if you don't like movies that are based on the end of the world being funny, you probably won't like it. But I really enjoyed it, and I thought the way they finished it was very clever. And they've sort of taken a bit of creative license by having a character in there who's a super rich nerd who is also funding space programs. Funny that. He also pays for the political campaigns and is a big supporter of the president. So, what he says goes, she doesn't get to make any decisions. So it's all centered around that philosophy. And the story starts with a student astronomer making the discovery of this comet. Now, I suspect, Fred, if this really was to be a case of Earth being struck by a 5 to 10 kilometre wide rock, more likely would be a mainstream organisation that would find it rather than a student astronomer, but never say never.
Mainstream organisations have student astronomers as well.
Of course.
So excuse me. It the whole issue of near Earth objects was basically ignited, if I can put it that way, by colleagues of mine in Edinburgh back in the late 1970s, who were pointing out the possibility that the Earth's history has been changed by asteroid impacts, and that was then picked up and basically became, a big ticket item when it was established beyond reasonable doubt that the demise of the dinosaurs, the Cretaceous Tertiary, as we used to call it, event 66 million years ago was almost certainly caused by an impacting object. So that focused attention in the very early 1980s, and since then it's been taken increasingly more seriously. I guess the turning point came at the end of the 90s when, if I'm remembering my dates correctly, when the US Congress mandated NASA to find effectively all objects that could threaten the Earth, which were bigger than a kilometre in diameter. And they did that. Now, you can never make it all of them because this is always a statistical thing, but the mandate was actually, I think, 95% of all objects bigger than a kilometre in diameter should be known, and that happened. Those are the ones that could cause planet-wide effects. They probably wouldn't kill off humankind, but they would certainly cause planet-wide effects. So now NASA is working on detecting all objects bigger than 160 meters, I think is the current number. The same sort of thing, 95% of all objects bigger than 160 meters. And the fraction is certainly not 95% yet, but there is a significant fraction statistically of all those objects that have now been discovered. So we're still in the fact-finding part of this process, Andrew, although, of course, that has not stopped scientists working on how you would deal with the idea that there was going to be an object that would impact the Earth. How do you deal with it? It would be. I mean, if it was a big object, it would be one that was probably known about already because it falls within that, the size range that that NASA have already found 95% of objects with. And so then for that, on that regard, you've got a long warning time. We know at the moment that no known objects bigger than actually bigger than 160 meters, I think, no known object will hit the Earth within the next 100 years. So you've got a long time, and that then allows you to do things like what the DART mission is trying to do. The DART mission is directed asteroid redirection test, I think it is.
Right.
Directed.
Oh, that's right. Yes.
Yeah. So it's just to nudge an asteroid and see what happens, and that's a really interesting experiment because it's the first step in this defence of the Earth if we really need it to do it. The in some ways more likely scenario is the kind of thing that happened at Chelyabinsk back in 2013, where an object maybe 10 meters across, 20, perhaps even 30 meters across, hit the atmosphere, detonated in the atmosphere and over a city, in fact, and caused this brilliant flash that sent everybody rushing to their windows to see what had caused it, and followed 90 seconds later by the sonic boom that smashed all the windows and injured lots and lots of people. That's something that is really hard to defend against. If we'd had longer with the Chelyabinsk object, and you know, it was tiny. It was, as I said, 10 to 30 meters across. Then you could have put civil defense measures in place, get everybody out of the city, or at least warn them that you don't go and look at the windows if there's a flash.
Don't look up.
Don't look up. That's right. Exactly that. So there's at the moment, we're kind of approaching this from two levels. The large object level, where you've got to move something to get it out of the way because you've got lots of time, or the small object level, where you really just want to safeguard people's lives because of something you really can't do anything about. The other part of the question is which countries are responsible for these things. So there is an international body, which is UNOOSA, the UN Office of Outer Space Affairs, and one of their subsidiary organisations is COPWAS, the Committee the Committee of the Peaceful Uses of Outer Space. That's right. Gosh, I deal with that organisation not quite on a daily basis, but certainly through my colleagues on a monthly basis, and it's terrible that I have to stop and think about what it means. So these are the committees there. There's COSPAR is the Committee for Space Research. That was set up in the very early days of the space age. And these are the international bodies that would be involved with this. There are a lot of the work is delegated in a sense to national bodies. So, for example, the idea of looking at or registering the near Earth objects, actually following up with measurements of them, that's basically the Minor Planet Office. I think there's a separate Near Earth Object Office now, which is within the United States. So it's the science agencies in the United States support that, and they do a fantastic job with all the work of actually working out where these objects are, generating what we call ephemerides, which are the tables that show you where an object is going to be at any given time, and it's the ephemeris. That's the thing that does that. That's what tells you whether there's going to be a collision or not within the levels of certainty. So there's a lot going on, and I guess you lump all of this under the heading of planetary defence. There is clearly more that could be done. There's more that we'd certainly need to do if we did find an object that was coming towards us. So it's not something, I think it is actually a case in which the politicians do actually listen to the scientists. So unlike most disaster movies, which seem to start with politicians not listening to scientists, this one probably would work out all right.
Okay, I'm sure you're glad you asked. Yeah, you asked the question, Alex. But thanks for sending it through to us.
Yeah, sorry, it was a long answer there, Andrew.
No, that's fine. But I'll just relay one more piece of the film for the benefit of the audience. When Leonardo DiCaprio and Jennifer Lawrence characters finally get in to see the president, they say, look, there's a 100% chance that this is going to destroy the Earth. We're doomed. What are you going to do about it? And they got into a conversation. And then Leonardo DiCaprio and the chief of staff says, is it 100%? I mean, 100%, you can't ever be certain about anything. And the conversation goes on. And Leonardo DiCaprio's character at one stage says, look, 98.7% certainty that this is going to destroy the Earth. And the chief of staff says, so it's not 100%. There was his fail-safe. We don't have to worry about it now. It's
not 100%, yeah.
Yeah, fascinating. All right, thanks, Alex. Lovely to hear from you. One more thing before we go. Got a joke sent through to us on Facebook from Judd. I think Judd sent us jokes before. A neutron walks into a bar and asks, how much for a drink? The bartender says, no charge for you.
I love it. Yes, I love it.
Yeah, yeah. I had to look up why that was funny.
Oh, did you? Okay.
No,
Don't tell him that. I wouldn't tell you if I had to look it up to see why it was funny.
oh, dear.
Yeah. No,
Anyway,
that's good.
that
Great
brings
stuff.
us to the end. Fred, thank you so much.
That's a pleasure. And we'll speak again soon, I hope.
I hope
If anybody's bothering to listen. Yeah.
And thank you for your contributions. Thank you for your questions. If you do want to send us a question, we're actually short on audio questions at the moment. Go to our website, spacenutspodcast.com or spacenuts.io. Yeah, that's right. And just click on the AMA link and you can send us a text question or an audio question, or you can record your question through whatever the thing is on the right. It's a little purple button. Don't know why it's on its side, but I guess that's supposed to be a space kind of analogy type scenario. Don't really know. I didn't design it. But yes, if you want to send us an audio question, we could use a couple, so please do. Until next week, thanks so much and stay safe. And we'll talk to you again on the next episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.